Okay, yeah. So this is going to be our 19th lecture on power system operation and control, and this lecture is also going to happen on OPF, or optimal power flow. So in the last class we saw the basics of OPF. I'll just quickly recap before starting today's session. So we saw about So we saw about some basic of requirement why power flow was introduced in economic dispatch, and eventually the incorporation of power flow in economic dispatch is known as OPF, or optimal power flow. We saw that the complete state of power system is determined in an optimal fashion with respect to some tactical constraints in an OPF. So the keywords were complete state, optimal operation, and constraints. And in complete state, we found out that okay, whatever PG and V set points what we give in power flows are coming from this OPF problem. So the output of the OPF is actually the input of the load flow problems, right? So this is what we saw in the class, and then we saw about the technical constraints. Here we saw about the generator limits, the real and reactive power limits of the generator. We saw about the voltage limits as well as the power flow limits, and yeah, obviously the power flow limit on the line as well as the transformer are both we have to include in the OPF problem. We also saw about the objective functions. What could be the possible objective functions? You guys suggested many objective functions in the last class. There can be many other objective functions. So yeah, just to give you a quick example, there are two most popular objective functions which are often used, which is total cost of production and total system losses. And then we saw that the OPF eventually is written for all the branches of all the. So for all these buses, for each bus you have to write two power flow equality equations, which will be one for real power and one for reactive power. So for every bus you have to write that equation, right? So you can see from this that the two bus example what we solved using this Newton's first order and second order, it was nothing but a sample of an OPF problem, and the equality equations what we wrote in that, we wrote the real power balance equation. We ignored the reactive power equations, we just included the effect of real power equations. So I hope now you can connect what we were doing before is actually nothing but solving an OPF problem. Saw about the inequality constraints, all the real and reactive power generator limits, voltage limits, and the line flow limits. And yeah, the objective function could be of this type, which is a quadratic type, similar to all economic dispatch objective functions. It can also be of quadratic as well as linear type. And here we saw means this the current OPF what we saw here is actually known as AC OPF. Can anybody tell me why we are calling this as AC OPF? Any? Yes, reactive power, voltage, if once you are including the effect of these two terms, we call it as ACOPF, right? And also we told in the last class that this is a non-convex model because we have multiplication of voltages with the trigonometric terms which are going to be non-linear, and eventually the problem becomes non-convex. So this problem, as I was telling in the last class, that this problem is really difficult to solve. Why difficult to solve? Because it is non-convex, non-linear, and as soon as you have non-convex, there is going to be multiple solutions for this problem, and as soon as you have multiple solutions, then it becomes really difficult to decide which solution to choose. And obviously when you have multiple solutions, then it's a debatable thing that then you cannot guarantee the solution which you are getting from the generators are correct, or it is correct, but it is unique, or it is optimal. It's a local optimal, or it is a global optimal. It is not, you cannot guarantee that. So as we cannot guarantee, then it becomes really a debatable thing. Now, as I told you that this is a very difficult problem to solve, and I'm sure I'll be giving you one example in tutorials, and you'll be able to see that just to solve a simple ACOPF problem, let's say even just for if I let's say do it for, let's say for 5 or 4 bus system, or let's say 10 bus system, or let's say if I go beyond that, let's say 30 bus system, there are few benchmark systems. If you run just ACOPF in these just 4, 10, 30 bus systems, these are very small compared to the practical systems, and just to run OPF problem on these small systems is also very difficult. Difficult in the way it is a time-taking process, and obviously once you solve it, you will see that okay, it is going to take a lot of time. Even if we ignore the time, you cannot guarantee the optimality of it. So that is also a big difficulty on this. Now, so how do we, anybody has idea, how do we use this in practical system? What is, now I already talked about this ACOPF. What is the practical use of ACOPF? Can anybody guess? Where in power system, in which situation in power system this ACOPF is implemented? What is the practical importance of OPF? Anyone? Am I audible to all of you? Yeah. So what is the practical relevance? We discussed on in depth in the last class. Just give it a guess, no problem. What is the practical relevance of OPF? One, you can say that I'll give you a hint in one of the as one of the importance, that we run load flow, and obviously to run a power system, assuming that you are sitting in a control center and you have to run a power system, you have to run load flow, and that load flow you have to run multiple times. At every, probably in every 1 or 2 minutes, you have to run a power flow. So, and because PMUs are there these days, we are going to see the SCADA systems later on in this lecture. But you know, those PMUs are there, a lot of measuring devices are there, and they transmit the data on real-time basis at the control center, and once the control center gets that data, it compiles all the data and it feeds in that data in power flow, and then he runs power flow continuously. And the voltage set point and the PG set point in power flow is coming from this OPF that we saw in the last class. So basically that is one practical importance, that OPF gives the PG and voltage set point of the generators, and based on that we run OPF. Other importance. Yes, good, minimize the cost, but minimize the cost where? When do we want the cost to be? Huh? In power plants, in a way yes. Power plant uses this optimization model to minimize the cost of its generation or production. And also system operator, we discussed about independent system operator and transmission system operator. Those system operators, they also use this model to actually get the minimum dispatch. So what we used to do in economic dispatch, the same importance goes here, because who runs that economic dispatch? System operator runs that. So system operator also runs this OPF to get the minimum cost of production. Now, can you guess what is the difference between economic dispatch and OPF? Because all those practical importance what you see in economic dispatch, the same thing is valid for OPF also. Right? So cost minimization, or even we can have loss minimization, we can have many other objectives what we can work on, but eventually let's talk about economic cost minimization. So then what is the difference between economic dispatch and OPF? I think now it should be clear to all of you. What is the difference between economic dispatch and OPF? Good. Yes, transmission network is not considered. What else? Reactive power. Reactive power for what? Yes. So the same you can get from OPF also, right? Here also you are seeing this value is nothing but the power which you are delivering in OPF. So, but then what is the difference between OPF and economic dispatch? One, what you said is correct, that reactive power is considered. What else? Yes, voltage also plays the bigger role. Voltage is also there, and transmission constraint, the third one is the transmission constraint, which actually is not there in economic dispatch. So in economic dispatch, if you run the economic dispatch, whatever dispatch you are getting, if you directly implement the value of PGs in practical power system, then there might be some transmission lines which will violate the limit or the maximum power flow which it can take, and the power can go beyond that value. Right? So these three parts are missing in economic dispatch, and these three parts we have considered in power flow. And with this OPF is more realistic, considering more practical information, because in economic dispatch we are also not talking about voltage. We are not talking, so voltage can create a big problem, right? Because if let's say voltages are going, either it is over voltage or it is lower voltage. in both cases, if it is over voltage, then your household appliances will get damaged. If it is under voltage, your appliances will still not work efficiently. So in both the cases, that issue is there. I'm not sure if you have observed it or not, that if the voltage is very low, then generally your air conditioners and your refrigerators stop working. They do not operate properly. And if the voltage is very high, then especially this affects the bulbs, the light bulbs. You will see that the brightness of that light bulb increases drastically if the voltage is very high. So that is a very risky thing, because the bulb can get damaged, right? So these three informations is added on economic dispatch, and eventually this model is known as OPF model, right? Now we got both the ideas. One is that the OPF is an important model, and it has a significant improvement from economic dispatch. Everything we got. Now the issue, what I was explaining in the start of this lecture, is that this OPF is difficult to solve. Now obviously there are a lot of importance is there, but now as it is difficult to solve, what we will do with these important features, even if these are important and we agree that this is important, but if we are unable to solve it, then what is the importance of it, right? So we have to basically simplify this problem in such a way that we compromise on the least of these features, and then we can still achieve a final problem, a final OPF model, which is still solvable. So if I just wanted to connect you from the research, if you see, most of you have also taken some term paper also in that. There are many papers in research, in literature. They talk about the simplification or simplifying this OPF model for practical usage. You can search, you will find a lot of papers in that, and all these papers are very important to us, or to this problem. And you can understand that this is really important to consider the QG, it is really important to consider voltage, and it is also important to consider this transmission constraints, and we cannot ignore that. So therefore there are a lot of papers, lot of authors, lot of researchers working in this area, including myself, in this direction to simplify this problem. But still nobody is able to do it. It is still a challenging problem. It is still a research problem which is still nobody is able to solve it. But what we can do is, one such assumption is, let's say voltage. Let us talk about voltage. I'm sure you have solved the power flows, and in the power flow you must have observed that the voltage always remain close to 1 per unit, and that's why in power flow also when we start running power flow, the first initial guess of voltage we always assume 1 per unit, right? Because we know that the voltage is always going to remain close to 1 per unit, right? Plus minus a bit it can vary, but more or less it always remains close to 1 per unit. Now if the voltage always remains close to 1 per unit, we can actually ignore the voltage and keep in the complete formulation what you saw just now, we can keep the voltage as 1 per unit. Now if we have ignored the effect of voltage, then we can also ignore the effect of reactive power, right? Because reactive power, you know from the power flow that P and delta coupling is strong, and in Q and V coupling is strong. So if we are ignoring this voltage, then Q also we can ignore, right? Let us see this and see how we simplify this. So to simplify this, we will actually run This is actually incorrect. I will not call it as direct current. It is actually called direct current in literature, but this is nothing but a linear OPF. We are deriving this linear OPF, which is nothing but some assumption, some simplification we are adding on this AC OPF to arrive at a simplified version. Let us see this simplified version in today's class. Now, at this I told that the previous model is AC OPF. AC is nothing but alternating current optimal power flow, because all reactive power and voltage related constraints are considered. Now, this linear OPF, here we are only representing the transmission system constraints. So basically, if we ignore voltage, considering that the voltage is close to 1 per unit, as we have already ignored voltage, we can obviously ignore reactive power also. But this transmission system constraints are still very important. So what we are doing, we are not going directly from economic dispatch to AC OPF, because AC OPF we cannot get a solution. In economic dispatch we can get a solution, but still few things are ignored. So a compromise is that if we can add this transmission system constraints somehow in the in the economic dispatch, then that model will be a very good model to solve, because one issue will get resolved, right? And this is done using DC power flow. I'm not sure, has it been covered in the computer aided power system course? DC power flow. Good. So DC power flow, then you all are aware of DC power flow, right? Because that way we only consider the change in delta is equal to change in power with respect multiplied by the admittance of the multiplied by the admittance matrix. So this is a very simple way. This way we can include the effect of transmission system constraints, and this is used in many studies. And this DC power flow, I'm sure you must have observed that DC power flow give a good approximation of AC power flow. So analogously, we can also say that the DC OPF also give a good approximation of AC OPF, because DC is nothing but linear. We'll see the model here. I'll give you the derivation also. It is much faster, much easier to set up and solve. So let us see the derivation of DC OPF. How do we do that? So basically we saw that the power balance equation is like this, where PG minus PL is equal to VI, VK, YIK cos delta I minus delta K minus theta IK. This is written for all the buses, and then the similar equation is also there for the reactive power, right? So these two equations are there. Now first step is basically we ignore the reactive power equation. So we'll ignore this equation. We'll ignore this equation, and what we'll do, we'll assume that the voltage is approximately close to 1 per unit. Now once we ignore this equation, only this equation is there, right? And we have also assumed voltage is close to 1 per unit, so you will ignore the effect of voltages. So I'll keep all the values of voltages as 1, right? Now we have just YIK cos delta IK minus theta IK. Delta IK is nothing but this part, delta I minus delta K. Okay. Now in this, let us expand this cos term. Let us open this cos term. So this cos term, once you open, you will see that cos delta IK cos theta IK plus sin delta IK sin theta IK. Do you agree with me? Now in this, YIK into cos theta IK is nothing but the, means when you write y you can write as G plus JB. G plus JB is basically the susceptance and conductance and susceptance of Y matrix. So it is nothing but Y, G is nothing but Y cos theta, B is nothing but Y sin theta. So Y into cos theta will be G ik, and Y into sin theta will be BIK. So let us put these values. It will be like this: GIK cos delta ik, BIK sin delta ik. Right. Now let us take this equation to the next slide. In this, we in the transmission system, we know that the R by X ratio is actually very small. Right. That means R is very less compared to X. Why? Because X generally in transmission lines they are of the length of the line is really big, probably 100 kilometers, 200 kilometers, and those lines have because of this, I'm not sure if you remember the GMD or GMR concept, where the effect of earth actually creates the capacitor type of connection, that the wire and the earth makes two plates parallel, which is like creating effect of capacitor, which actually increases the value of X drastically. Although the resistance of line is going to be fixed, but X increases at a very high value. Eventually R becomes much smaller than X, and if R is much smaller than X, then you can ignore the R, and if you ignore the R, that means even G will also be much less than X, right? Do you agree on this, right? So once you ignore the effect of G, then we will get finally this equation. We will get this equation is Pg minus PL is equal to summation BIK sin delta ik. Right. Now let us take one more assumption here, that the delta ik is what? Delta I minus delta K, right? This is delta ik. Now in transmission system, you must have observed this in power flows if you have executed that the angles or the angle difference between two buses are generally very small, very small. And if the angle difference is very small, then you can write sine delta approximately equal to delta. Right, this you know from the basic mathematics. We can write sine delta approximately equal to delta, which will eventually give you that finally the equation will be PGI minus PLI equal to BIK delta IK. Now this equation is a linear equation, right? You can see this, right? This is now a linear equation. Do you agree with me? Now this equation is a linear equation, or you can simply write it that Pi is equal to BIK into delta K. Pi is nothing but this is this part, the PGI minus PLI. Right. Now this becomes a much simpler equation. This is a linear equation. So in economic dispatch, we were only considering the cost and the power balance, which was nothing but the sum of generation should be equal to sum of demand. Instead of that, we will now use PGI minus PLI is equal to sum of BIK delta IK, and this will be written for all the buses in the power system. With this, now if I have to add this equation in economic dispatch, which will eventually lead to the DC OPF, let us see how does it look. So the DC OPF model looks like this. This is the cost function. It is same in economic dispatch. Instead of power balance equation where sum of PG equal to PD, I am writing this, which is Pi is equal to Bik delta Ik, right, for all the buses. This equation is again same in economic dispatch, which is nothing but the generation limits. Now there will be two or more new equations. One will be delta. So delta should be remain within some limits, and this delta, practically any idea what limit we keep for this delta? How much angle should we allow? This comes from the equal area criterion. Anyone knows that? Yeah, 90 is theoretically yes, but practically anybody has idea how much we can do? Okay, means okay, yeah, you are right. 70, 80. It depends on the country to country because different regulators have kept different margins for this delta. But in India, I can tell you this delta is kept between 30 and plus minus 30 degrees. So it is kept between plus minus 30 degrees in India. But obviously, different country has its own regulation. Everywhere it is used separately, because beyond 30 there is always a risk that it may lose its stability. So generally beyond 45 it will lose stability, so generally they keep somewhere between plus minus 30 degrees. Right, now there will be additional equation that all these issue or all these process, why we did that. The major reason of doing all these issues was this constraints, which is nothing but the power flow constraints. If we have formulated this equation, now you know that the power is between two buses is based on this angle delta I minus delta j, and the Bij is nothing but the admittance matrix, and this will give you the power flow Pij, and this power flow should remain between minimum and maximum. Minimum is nothing but the minus of the max. So this you have to implement for all the branches, for all the Ij belongs to the branches, so all the branches. Now you can see in this model that this model is actually a this model is having, it is a complete economic dispatch. Only additional thing which we are adding is the transmission line constraints, and obviously number of variables have also increased. In economic dispatch, number of variables were just the PG values. Now the number of variables are, we also have this delta I as the additional variables, right? So if let's say, that I'll come later on. So you can see here that we are adding this line limits. So basically here, this model, you can also call it as DCOPF, you can also call it as SCED model. So if let's say you are seeing some of the means documents of the regulators of different countries, like in US, Canada, Europe, Australia, even in India, people mention SCED and not DCOPF. So everywhere you will see the term SCED, not DCOPF. It is very rarely used. The most common terminology is DCOPF, SCOD. But DCOPF is used in literature. In research, people always use DCOPF, but in practical regulatory system, people use SCED often and compared to DCOPF. So now you got the idea why this model is called SCED, and now you can see that this model is linear. Means yeah, constraints are linear, although objective is quadratic, that is fine. Now you can see and tell me that this problem is convex or non-convex. This problem is convex or non-convex? Yes, yes, it is convex. Yes, because it is all linear, so it is convex. So now it is, and if it is convex, then there is always going to be just one optimal solution, which will be nothing but the global optimal. So this will be a global optimal solution. So this is going to be a global optimal solution, and this will be basically this solution will have just one answer or one solution, and this will be very easy for system operator to give it to the generators to inform the loads, and everything will be unique, everything, because now you just have just one answer or one solution. So this becomes very easy to solve and to get. So you can easily solve it using MATLAB and get the solution, right? So for solving this, the procedure is always going to be the same. If let's say the problem is linear, if the objective function is also linear, then you can solve it using linear programming method. If the problem is quadratic and this constraints are linear, then you can solve it using this Newton's method, Newton's first order or second order, and you can solve this problem. Also you can solve this using KKT, where you can take different conditions, because for KKT you have complementary slackness condition. So I have not given any example for KKT, right? Only one example in the class I gave you, that you have to see that complementary condition, that if it is satisfied or not. So you have to make different cases, and based on those different cases you can solve the problem, right? I hope it is clear now, this concept of DC OPF. Now let us see some examples. So let us take the same example of 3-bus which we have solved before. Here we were not, I did not give you any network. So this is the same example what we saw in economic dispatch, even the load is 850. Now here I'm just giving you this network diagram, and I'm adding here loads L1, L2, L3. So let us distribute the load also. So let's say because it's 850, right? So let us make it 400. L1 is equal to 400 megawatt. L2 is, let's say, 300 megawatt. It is right, 700, right? So 150. So L3 is, let's say, 150 megawatt. Right. Now you have to run it optimally. Run an OPF here, DC OPF here. Do not run AC OPF, just run DC OPF, and then tell me what the power flow is going to be. P13, P12 and P23. So this you have to run it. This is going to be a tutorial problem. You can run it and you can tell me the answer, right? So this we are going to see in the tutorial, because this Wednesday we are going to have quiz. Probably I can give you just quick example on this. You can solve it, and then this will give you a quick understanding how we can formulate this part. Also, just wanted to give you another information here. So how many variables are going to be there for this 3-bus problem in a DC OPF? How many variables are going to be there? Can anybody guess? What all variables? What will be those variables? Can you tell me? No, PG1 will be there, one variable. PG2 will be one variable. PG3 will be. So 3 are there itself, but there will be more variables apart from this. Sorry. No, these are not the variables. These are this will be calculated afterwards. What are variable? 8 means how many? Means what are these variables? No, because we are solving DC OPF. We have ignored now the voltage and reactive power. No, ignore the dual variables. Ignore the dual variables. Just the primal variables. Yeah, but how many? So how 5? Yeah, you can keep one slack. So basically one variable for PG1, here PG1 will be there, one variable for PG2, one variable for PG3, right? And then assuming, because delta, you can take this first bus as a slack bus, so you will have delta 2 as one variable and delta 3 as variable. So there will be total 5 variables, 3 PGs and 2 deltas, and based on that you can optimally calculate all the values. So let me simplify the problem. Let me simplify the problem and let us quickly discuss that before we close today's session. Let me just quickly erase it. Yeah, please. No, but this is an optimization. Optimization, you will get it automatically. Here we can get it automatically. So let me just let us see. Just ignore the 1 second. Let me just say, let's assume the cost function of all these generators. Ignore this part. Ignore this part. Only this is the cost function of the generator 1. Ignore this part. Ignore this part. This is the only the cost function of the generator 2. Ignore this part, ignore this part. This is the only cost function of the generator 3. You know now all the power, this generator's upper limit, lower limit. Now if, let's say, if I tell you that there is only 2 generators, generator 1 and generator 2, there is no generator 3. Just assume for a while there is no generator 3. What will be the optimal solution? Or rather, just keep all 3. Don't worry. Just keep all 3. G1, G2, G3 are there. Now what will be the optimal solution? What will be the solution of G1, G2, G3? No, I want the value. I want the value. How this optimization works, because I think there is a bit of confusion here. What will be the value? How can we decide what will be the value of the generators? This is the setup. Right, now you know that the 400 megawatt is the load at the bus 1, 300 megawatt is the load at second bus, 150 megawatt load is at load 3. I am asking what will be the optimal value, and now the objective function is just this one. For the first generator it is 7.2 into P1, second generator it is 7.85 into P2, and the third generator is 7.97 into P3. What will be the optimal value of PG1, PG2, PG3? Any idea? How do we calculate the optimal value? Okay, let me rephrase my question. I think it is becoming very confusing. Which one is the cheapest generator among these 3? With generator 3 or generator, yeah, generator 1 is the cheapest generator because 7.2, it is just asking 7.2 rupees per megawatt. It is asking 7.85 rupees per megawatt, and it is asking 7.97 rupees per megawatt. Which one is cheaper? One, right? I hope everyone is agreeing on this. Now, let me ask you another question, that if let's say the total load is so obviously now let me ask you, if let's say if we want to start generating the system at a minimum cost, at an economic operating cost, then which generator should start running first? Yes, exactly. So generator 1 will start generating first. So generator 1, what it will do, it will start generating, increase its generation from 150 because its minimum limit is 150. It will keep on increasing, and obviously it will see that it will reach at 600, but it will not be able to still satisfy the load of 850 megawatt. Right? So this generator PG1 will generate at 600 megawatt. Now it has exhausted. There is no more power remaining with generator 1. Now which generator to choose from G2? Why? Why to? Exactly, good. So the next cheapest, we have to find the next cheapest generator, and the next cheapest generator here is P2. So we will pick this generator, and because we just need, because total load is 850, remaining is 250, so this generator can generate between here, which will be 250. So this G2 will generate 250, right? And with this the load is balanced. What will be the value of PG3? What will be the value of PG3? But its minimum limit is 50, right? How can it be 0? No. I mean, see, I was just thinking, means I was trying to confuse you guys. That's why I said that. So basically, what will happen, that this generator, the second generator, will not operate at 250. It will operate at 200, and the third generator will operate at 50. Because this is the costliest generator, but this generator we will try to fix at its minimum value. If let's say the minimum is 0, let's say ignore this part, let's assume minimum is 0, then what will happen, that this will generate 250 and this will generate 0. Let me quickly erase it. So yeah, this will generate 0, right? Clear? Now if the minimum limit of the third generator is 50, which we are anyway seeing that this limit is 50, now what will happen is this will go to 50, right? Because we cannot go below 50, it has to remain at 50, and then this generator will generate 200. The second generator will generate 200. Do you agree with me on this solution? Why we are, Good, right. So do you agree with me that P3 will always remain at its minimum value at 50 megawatt? Because obviously it's a costliest generator. So therefore, and because the P min of the third generator is 50 and not 0 megawatt, so we have no option. We have to run it at 50 megawatt, and P2 will generate 200 megawatt. Yes, please. But it is the data, right? Because P3 has given the data that I am going to generate minimum 50. In practical only. This is a practical situation. Practically, generator gives a minimum generation of 50 megawatt. They never say that Means they can say that they can generate 0 megawatt, but they also give 50 megawatt also. Okay, so what means I can tell you, because this we are going to see later on in this course. I'm not sure if you know about unit commitment or not. Are you aware of this? Okay, because we are going to see this in practical. What we do, we will actually switch off this generator, right? Because its Pmin is 50 megawatt. If you are keeping this generator on, then you have to operate between this 50 and 200 megawatt. You cannot violate this. So the best solution, you are right that it is an uneconomical solution. The best solution will be to switch off this generator, and this switching off, on and off, we will see in the later, probably after your midterm, we are going to see that how we switch on and off these generators. But just wanted to give you this understanding that these generators are generally switched off. But even then, if it is switched on, you have to operate within its minimum and maximum rate. You do not have, you cannot, if its Pmin is 50, you cannot tell them to operate at 0. You cannot do that. It has to operate within its limit. Right? Clear? So now let's assume here the Pmin is nothing but 0. So then if Pmin Z is 0, then this P3 will become 0 and this P2 will become 200, right? So this will become 200. Now what will be the power flow on this line? Assuming all the reactances are same, I did not mention that. Assume that the reactances are same in all the lines. So X of all the lines are same. X12 is equal to X13 is equal to X23. All are same. Let's take, I'll just give you the value 1 per unit. Let's take 1 per unit. Any value you can take because it's all same. 1 per unit. Now my question is, what will be the power flow? So right now PG1 is generating 600 megawatt, PG2 is generating 200 megawatt. Sorry, it will be 250. Why I am writing? Because load is to 850, right? So PG2 will be generating 250, PG3 will be generating 0. What will be the power flow? Even without knowing the value of angles, you can tell me the value of power flow. No, power flow. So what is the value of P12, P13 and P23? What is the value of P12, P13, P23? Just apply, think logically from the, you must have studied Kirchhoff laws, right? Kirchhoff laws, we write nodal, which one? P12, P13, P23. How did you calculate it? No. Basically what will happen, let me just quickly erase few of the things, or I'll write it here. Basically, so let me just quickly write, okay. P12 plus P13, what will be the value? If you think from the first bus, whatever power is coming in and whatever power is going out, that will be the power will be flowing on P1 to P13, right? So power balance has to be there, right, at every bus. So 600 megawatt is being generated 400 megawatt is being withdrawn, so remaining is 200 megawatts. So P12 plus P13 should be equal to 200 megawatt. Do you agree with me? Let's take the sign convention. P12 is here, P13 is here, and P23 also here. You can take any sign convention. I am just taking one sign convention. Right. Now let us write the same thing for the second bus. Tell me the value equation for the second bus. So 250 is being generated, right? 300 is taken as a load. So that means equal to this will be minus 50, right? What will be on the left hand side? It will be, I can tell you, it will be P12. I'll not mention the sign because sign you are going to tell. I'll write P12, P23. What will be the sign here? So basically think from that whatever is incoming is positive, whatever is outgoing is negative. So P12 is incoming, it is positive. P23 is going out, it is negative. Yes, yes. Hello. Okay, okay. So basically I am not going into details here. I want you to tell me the values of P12, P23 and the value of P13, P12, P13, P23. P23 will be 0, okay. P13 will be 150. P12 is, you are telling it is going to be 50. Okay. Okay, ठीक है. This could be one of the solution. I'm not. Yeah, this is going to be the solution, right? So this is 150, right? Now you're saying P23 is going to be 0. Now if P23 is 0, then what will be the value of delta 2 and delta 3? We have assumed first bus as a slack bus, so delta 1 is going to be 0. So you know delta 1 minus delta 2 by x12 is nothing but 1 per unit is equal to 50. So you can calculate delta 1 is 0, so you can calculate delta 2. Similarly, you can do delta 1 minus delta 3 by x13 should be equal to 150, and you can get the value of delta 3 as well. Right? Let me actually derive all the equations, write it down for you in the next class, and so that you get the clear picture of it. How we do it, how we solve it, everything. I'll make it very clear in the next class. Okay? Is it fine now? Because I have already crossed my time. Let me do that in the next class. But you got the idea, right? Or is there any confusion here? Okay, let me actually give you a few more examples. Let us solve an example in the class only, without going into the tutorial. Let us solve an example in the class. So on the next Wednesday in the class, we will solve an example, and in the second half we are going to have quiz. right? So it is going to till on 14th lecture. I'll tell you in the morning till 14th lecture. From 7th to 14th we will see on the quiz. Okay, ठीक है. So let us